computer. So welcome everyone to our computational linguistics event. You see the screen, this like green outline thing disappeared. Anyways, hello. I guess we can just begin now. So here's the check-in code. We also put a link into the chat so you can get your code login. So today's agenda, we're going to be going over what computational linguistics is, some formal grammar, some probabilistic models, and then finally, the machine learning aspect, the data-driven approaches. So the big question is, what is computational linguistics? Computational linguistics is a really interesting field that focuses on the study of languages from a computational perspective. It's a widely interdisciplinary field working with anthropology, cognitive science, computer science, and psychology in order to understand language and solve problems related to it. While much of what we think and say is fairly natural for us humans, computational linguistics deals with how computers understand phonetics, phonology, morphology, syntax, semantics, and more. Next slide. So the larger purpose of computational linguistics is to solve and understand problems that deal with computer tasks related to human language. As language is such a large part of our society, this means that the scope of the field is quite broad. Things like spell check, machine translation, that predictive text that you use on your phone are all some applications of this work. And then this is the part where we say computational linguistics is also somewhat more mathematically based than computer science, but computer science is just applied math, so it's okay. So back before we were all born, machine translation was more rule-based and heuristic-based. Physics is yes, of course. So there was no deep learning-based speech synthesis back when the 6502 was a CPU that everyone used. So things like the speak and spell from ET. Actually, I don't know how many of you have even seen ET. Old people, I don't know. Well, the speak and spell relied heavily on things like a knowledge base to make coherent words, essentially like a long dictionary and rule-based set to generate the speech. But many similar technologies did the same thing, and it's still something that is done. Stuff like Siri and Google Assistant do deal with this realm, or do deal with the realm of natural language understanding through machine learning. But stuff like, say, what's the weather, returning a stock response, comes from a knowledge base. So it is still something that does happen. Furthermore, or I guess continuing on, as the internet boomed, one of the big things that happened is text became widely available. Large data sets, like huge data sets, exabytes in size, became available. And it became more reasonable to do computational linguistics and natural language processing models based off of deep learning. And computers became a lot faster. So one example of this is, say, the state-of-the-art natural language processing model, BERT, is something that is thrown around a lot. It is trained on the entirety of the English Wikipedia and Project Gutenberg, which is kind of insane. Like, just gigantic corpuses of text are now used for machine learning type data-driven models. So what about natural language processing? We've kind of thrown around that word as well. Well, computational linguistics deals with languages more formally and modeling what that entails. Natural language processing deals a lot more with the language we speak, say, what we message to each other, that type of thing. So just some definitions, essentially. These are very broad definitions, so take this with a grain of salt. So what makes computational linguistics quote unquote hard? First of all, human language is kind of awful in terms of like making sure the point is put across. So they're ambiguous, complex, fuzzy, or vague, heavily context-based, and rely on the understanding of the world as well as, say, social systems in order to understand what a sentence means. Also, human natural language is unpredictable at the best of times. Natural languages are always evolving. Let's say when you're messaging your friends, why or why not do you use punctuation? That's something that like you can consider. Slang is something that's cool. What is it? Portmanteaus are things that are always being created and randomly used. These are all things that make it such that simple heuristics aren't enough to understand meaning. Yes. So at this point, does anyone have any question? Or like, any comment, or anyone want to say anything? Just wave. Say something in the chat. Wave, thank you. Yeah. Okay. So now we're going to get into some of the, what's it called? The table of contents that I've lost. Well, let's continue.
Yeah. So, okay. So despite like everything we said about how human language is like really difficult, people still try to process language. So we're going to talk about methods that do that. One of the really like most basic, simplest ways that you can process text data is through regular expressions. And you probably might have already learned about this from CC 105. If you haven't taken CC 105 yet, you will, and you will learn about regular expressions. Basically, regular expressions are used to define regular languages in that class. But in the context of text processing, regular expressions are used to find matches to a pattern within a body of text. So basically like string searching. Regular expressions are pretty easy to implement and useful for processing consistently formatted inputs. So if you have like a lot of text and you know that it's going to be formatted in a very specific way, you can use regular expressions to parse that text and extract data from that. But because regular expressions are rule-based, they become pretty inflexible to like small variations in text. Like for example, if you want to process phone numbers from a body of text, and phone numbers can be formatted in a lot of different ways. So for example, you can separate the first 3 numbers with a dash from the other next 3 numbers, and then the second dash between the second 3 and then the last 4. So that's one way of formatting phone number text. But you can also format phone number text in a lot of different ways, like completely leaving out those dashes entirely, putting dots, maybe parentheses around the first 3, etc. And so if you have to account for all of these different variations, then the regular expression becomes really large and unwieldy. Also, regular expressions just completely ignore all aspects of human language. They treat all text as just like any text. They completely ignore the fact that we're processing language specifically. And this is something that future methods will take advantage of. Next slide. Okay, so part of speech tagging is one method that actually considers human language and how it's structured. Specifically, it considers how human language contains classes of words that each serve different roles in a sentence. And parts of speech are classes of words like nouns, verbs, and adjectives. One really common way and really well-known way of breaking up sentences into parts of speech is to use Noam Chomsky's formal grammar. It basically defines that sentences are composed of noun phrases and verb phrases, and that these phrases can be defined recursively according to specific rules. And again, if you've taken 105, this seems really familiar to a context-free grammar. So this is a way to sort of tag different parts of a sentence and assign them based on the roles they play in a sentence. So we know like very distinctly that the word the carries much different semantic information than the word bear does. So part of speech tagging can be useful for identifying important parts of sentences, and then they could also be used to build really simple question answering models as well. Next slide. And so these like 2 previous methods we've seen are all like rule-based methods of processing language. But at this point, computational linguists start to lean into building models based off of large data sets. And one really fundamental idea in data-driven models of language is the n-gram. And n-grams are just a way of breaking up text into phrases of n words. It's not really complicated, but the idea it captures is that sometimes there are sequences of words that are meaningful together and best represented as an n-gram instead of as separate tokens. So for example, the trigram we have here, please do not, that's a really common phrase that we'll see in a lot of text in English. And so that's something that carries semantic weight together as opposed to in pieces. And n-grams become directly relevant in one of the most well-known language models. Next slide. Markov chains. So Markov chains sound really complicated because the name Markov chains just has the name of the guy who came up with it instead of like a useful description of what it does. But if you have like a really basic understanding of state machines, you'll be fine. The general idea of a Markov chain is that the probability of the next word in a sentence depends on the previous word. And so normally you represent a Markov chain as like an n by n matrix that stores all the transition probabilities between words. But for like simplicity purposes, it's useful to think about it as a state machine or a tree-like structure. One intuitive way of using Markov chains is to automatically generate text. So like starting from some word, we can flip a coin to determine what the next word is, and then flip a coin again to determine what the next word is, and so on. This particular arrangement is called a first order Markov chain, meaning that the probability of the next word depends on the probability of the previous word. But you can also construct higher order Markov chains by having the next word depend on previous however many you want words. So these word transition probabilities can be set manually, but that wouldn't really be helpful for anything. So computational linguists look to determine what the probability values should be by training this model on a data set of text. For this first order Markov chain, you can look at every bigram in your text and then record how many times each word comes after every other word. And that method would give you the probabilities that that word occurs after this other word. And so this method provides an incentive for us to develop better ways of cleaning, handling, and pre-processing text data. Before we go to the next slide, I'd like to stop for questions because that was a lot of information. Any questions? Please wave. Okay, cool. So moving on to the next slide, we'll talk about ways of processing language data.
Okay, so before we get into more of the data-driven computational linguistics stuff and natural language processing things, one of the things that we do is to pre-process our data in order to reduce complexity. So why do we do this? It's because, let's say we want to compare two strings, let's say something like that. If we were to pre-process our strings, we can get a better, we can, let's say, reduce the forms of the words into something that we can more easily compare and make processing easier for us. So the main steps that we do are going to be lowercasing, removal of stop words, and stemming and lemmatization. So lowercasing is very simple, just taking, let's say, lowercasing all of our words. This is a thing of like vocabulary or a dictionary, just reducing the number of words if we were to differentiate something like a word with a capital and a word without it. Stop words are words that are generally just used a lot, but don't have any inherent meaning. Stuff like the, a, and, so. They are used a lot in our language, but say, what's the difference between a hat and hat? So we remove those in order to simplify our tokens or strings. And then the last part is stemming and lemmatization, which is also a method of reducing our vocabulary. Stemming is a fairly crude heuristic process that cuts off the ends of the words. So we can see some special cases like easily, which turned into easily with an I, but the point of it is essentially just to cut off the ends of words in order to make them more similar. So runner, run, and running all become, or mostly become this, running and run become the same, but runner does not. Similarly, runs and run become the same. The difference between runner and run are based off of part of speech tagging, which we talked about earlier. So one is a noun and one is a verb. So we do want to simplify all the verbs to be close together versus the nouns. That last part, okay, so lemmatization similarly does that. Wait a minute. Oh, wait, I think I messed that up, but whatever. Lemmatization is different in that it uses a more thorough dictionary in order, rather than just removing the ends of words in order to get the base form. Stuff like better turns into good, walking turns into walk. Why is ran not run? Because stemming only is meant to mostly just cut off the end. And there are a lot of, I want to say arbitrary, but I believe that there is probably a more thought out reason why these words are chosen. Stuff like the snowball stemmer and lemmatization method are very thought out, and there are papers based off of them that I have not personally read. So, but you cannot just cut the studies to studies. I'm not entirely sure what you mean by that. Like if it's just cut off. Well, the point of the stemming from studies to study is things like the word study by itself with a Y will then, we're trying to reduce the number of different words. So something like studies with an IES would turn into study with an I. Things like the word study with a Y would turn into study I. What makes studies different than study? Let's see. There wouldn't be any difference. So they would both turn into study with an I. And then ran versus run is mainly just a special case, I believe. We'll continue and then we'll come back to this point when we end the recording so we can like discuss this a little more if you have more questions. But yeah, lemmatization is more context-based in terms of like, while stemming can use part of speech tagging, lemmatization can moreover use a more advanced version of that based off of the package you use in order to figure out what is a more appropriate method of reducing to its base form. Yes, saw turns into see, something like mice turns into mouse. There are more examples like this, but I'm not entirely sure, but we can try that later. We have some tests or tests pack, or what is it? Just a Jupyter notebook that we can run. If we go to an example, something like this, the Gary professionalism, or what is it? A part of the Gary professionalism copy pasta. Things like professionalism turn straight into profession. The point of this, it may seem really rough, where we've taken a fairly long sentence and like kind of destroyed it. But if you look carefully, we can see that we haven't actually lost a lot of meaning. And the reason why we want to do something like this is mainly in order to, when we're extracting features from this, from our example. So if we go to our next slide, the point of all of this is to turn our strings into numerical vectors. So why do we want to do something like this? Essentially, what is it? We need to represent strings in some numerical forms in order to make comparisons and also in order to find similar feature vectors. So in our example, we have some French, but if we were to say the word king, this is a very famous example of king minus man plus woman is equal to queen. If we take the vector of our extracted, if we extract the vector from the word king and we extract the vector from the word queen, they're very similar. And the difference between king and queen is similar to the difference between man and woman. So we are able to do some numerical calculations in order to find relations between words. Does anyone have any questions about this? This is kind of like a pretty abstract concept. So essentially what happens is that this is the part where we get into like deep learning, which is just its own bag of confusing nonsense. But what happens is we have a model that is trained on a corpus. we get like a corpus of text, and we train a model to essentially figure out what is important and extract features from a string. And what we mean by features are like specific parts of, or specific relations that are, say, more important than others. And when we went back before to our preprocessing, when we got rid of, say, words like the and a, and reduced the number of like different words, we essentially made it so our feature vector could more accurately pull important features. Well, the difference between, say, like course and course. So what's the difference between courses and course? And also words by themselves are pretty arbitrary. So what is the difference between, say, the word course with an E and the word course without an E at the end? And to a computer, it really doesn't mean much. So if we cut it off essentially just so that we have fewer words, not necessarily because the word course is a long word, but because there's courses, there's what is it? I guess we're trying to reduce all of these different words to a similar base in order to in order to reduce complexity. Yeah. So one of the applications of feature vectors is something called machine translation. Modern machine translation encodes a text or a string into a feature vector and decodes it by having another, we essentially train a model to turn our sentence into a feature vector, and then we train a decoder to find a similar vector in the other language so that we can extract the text into the different language. So we, extract a feature vector from the text using the encoder and then decode that feature vector into another language by training the decoder. This is something that's been, this is heavily feature-based. It's a very abstract idea too, but it's quite an interesting conundrum to it's, wait a minute. Does anyone have any questions about this? It's like, we're just kind of glossing over this because we want this to be more of a survey of the field. But yeah. Okay. Next, we have, this feels like linear algebra transformations. Well, essentially, modern machine learning is mostly just linear algebra and calculus. So there's that. Next is TF-IDF, term frequency inverse document frequency. So what this does is essentially, it's something that's often used in search engine optimization in order to find the importance or uniqueness or relevance of a word in a corpus of documents. So when we have a lot of documents, how do we determine what are important words in these documents? So if we say something like the word the appears many times in every single document, which means overall, it's not a very important word. However, if we say have a document that has the word dog in it many times, and every other document doesn't often use the word dog, that means we know for that document, the word dog is a relevant term. And we can calculate that and have a pretty objective numerical heuristic. So this is often used in search engine optimization in order to, say when you search for a term, retrieve documents that are relevant to that instead of just, what is this doing? What if the guy just like dog analogies? I'm not sure. It's often used in search, because you want texts that don't have a ton of just repetition and unnecessary like phrasing. So like what is another term that we think of when we rank low because it appears many times in many documents? But say something like bug or like frog, or phone, these are we can kind of extract importance of these words from these documents. compared to other words. Yeah. Okay. That's it for now. Does anyone have any questions? Well, we did exactly hit that 30-minute mark. So we have, what is it? We have 15 minutes. I put us like, what is it? For our thing, we had 35 minutes of presentation and 15 minutes of questions. Does anyone have any questions that you have? I guess I can end the recording now too.